a galaxy that shouldn't exist. When the James Webb Space Telescope stared into a patch of empty darkness, it found JWST 14-0, a massive, bright galaxy just 290 million years after the Big Bang. The most distant object we've ever seen, and way too mature for its age. It wasn't alone. JWST quickly spotted more universe breakers, huge galaxies with stellar masses up to 100 times what models allowed, appearing when the universe was only 3 to 5% of its current age. Oxygen showed up impossibly early. These weren't fragile infants. They were already cosmic heavyweights. 3 years in, JWST keeps rewriting the rules. The early universe was busier, brighter, and more advanced than we ever thought. Our 93 billion light-year observable bubble? Maybe just a tiny corner of reality. If these cosmic plot twists blow your mind, smash like and subscribe, hit notifications for more mind-bending JWST discoveries. The universe is wilder than we imagined. Let's keep watching. The James Webb Space Telescope launched on Christmas Day 2021, carrying humanity's most ambitious attempt to peer into cosmic history. Unlike its predecessor Hubble, which primarily observes visible light, Webb was designed to see in infrared, the stretched wavelengths of ancient light that has been traveling through expanding space for billions of years. Its mirror spans 6.5 meters in diameter, composed of 18 gold-plated hexagonal segments. That's 2.7 times larger than Hubble's mirror, giving it about 6 times the light-collecting area. But size alone doesn't explain Webb's revolutionary capabilities. The telescope operates not in Earth orbit, but at a gravitationally stable point called Lagrange Point 2, nearly 1 million miles from our planet. There, shielded by a tennis court-sized sun shield that blocks radiation from the Sun, Earth, and Moon, Webb's instruments cool to temperatures approaching absolute zero, cold enough to detect the faintest infrared whispers from the universe's earliest moments. When Webb stares at what appears to our eyes as empty darkness, it's not searching for nothing. It's waiting. Waiting for individual photons that began their journey when the universe was young. Photons stretched almost to invisibility by cosmic expansion. These photons arrive slowly, sometimes one at a time, carrying information from eras we can never revisit. Here's where our intuition about the universe completely fails us. The Big Bang occurred approximately 13.8 billion years ago. Light travels at 300,000 kilometers per second, the fastest speed possible. So logic suggests that the most distant objects we can see should be about 13.8 billion light-years away, giving the observable universe a diameter of roughly 27.6 billion light-years. That logic is wrong. The observable universe has a diameter of approximately 93 billion light-years, not 27.6 billion, 93 billion. The edge of what we can observe sits about 46.5 billion light-years away in every direction. This seems to violate the cosmic speed limit. Nothing can travel faster than light through space. And that's the key phrase, through space. Space itself has been expanding, and when distant galaxies emitted the light Webb detects today, those galaxies were much closer to us. But during the billions of years that light traveled toward Earth, the space between us and those galaxies continuously stretched. By the time the photons arrived, the galaxies themselves had been carried tens of billions of light-years farther away by by the expansion of space itself. Think of it like running on a cosmic treadmill. Early in the universe's history, expansion was slower and light made steady progress, but expansion has been accelerating. The treadmill beneath the photon's path keeps stretching, making the journey longer even as the photon runs at maximum speed. Some photons that started early enough manage to reach us. Others, emitted from galaxies now beyond a certain distance, never will. Not because they run out of time, but because the space they must cross grows faster than they can traverse it. This creates what astronomers call the cosmic horizon, not a wall or an edge, but a boundary of information. Beyond approximately 46.5 billion light-years, space continues. Galaxies continue forming and dying. Black holes continue merging. Entire cosmic histories unfold. But their light can never reach Earth. Not because our technology is inadequate, but because the fundamental structure of space-time prevents it. When Webb began its deep field observations, astronomers expected to find the universe's first galaxies appearing as dim, primitive structures. Cosmic infants taking their first uncertain steps. What they found instead triggered a crisis in cosmology. In the first data from Webb's near-infrared camera, researchers identified 6 candidate galaxies at extreme distances, existing just 500 to 700 million years after the Big Bang. These galaxies weren't small. Some had stellar masses, up to 10 billion times that of our Sun. One galaxy appeared to contain a stellar mass 100 billion times that of the Sun, approaching the mass of our entire Milky Way galaxy today. According to standard models of galaxy formation, this should have been impossible. Galaxies form through a hierarchical process. Dark matter first clumps together in creating gravitational wells. Ordinary matter, hydrogen and helium gas, falls into these wells. The gas must cool before it can collapse under gravity to form stars. Each of these steps imposes a time scale. You cannot skip steps. You cannot suddenly assemble a massive galaxy without first going through earlier stages. Joel Leja, an astronomer at Penn State who modeled the light from these early galaxies, stated the problem bluntly: "These objects are way more massive than anyone expected. We looked into the very early universe for the first time and had no idea what we were going to find. It turns out we found something so unexpected, it actually creates problems for science." The research team nicknamed them universe breakers. If their masses and distances were correct, these galaxies would require changes to our fundamental understanding of cosmology, the science that explains what the universe is made of and how it has evolved since the Big Bang. As follow-up observations accumulated, part of the mystery began to resolve itself, but not all of it. Some of the brightest early galaxies turned out to be what astronomers now call little red dots. These aren't standard galaxies dominated by starlight. They're galaxies harboring actively feeding supermassive black holes. When matter spirals into a black hole, friction in the rapidly moving gas generates tremendous heat and light. This extra brightness can make a galaxy appear much more massive than it actually is, as if the light came entirely from stars. A 2024 study led by Catherine Chorowski at the University of Texas identified several universe breakers as black hole-dominated systems. When these objects were removed from the analysis, the most extreme cases of overly massive galaxies disappeared. Crisis averted? Not quite. Even after accounting for black holes, Webb's observations still show approximately twice as many massive galaxies in the early universe as the standard model predicts. The crisis has eased from catastrophic to merely deeply puzzling. Something about the early universe's star formation efficiency differs from what happens today. One possibility: in the denser early universe, it was harder to blow gas away during star formation. Today, when gas collapses to form stars, it heats up and creates outward pressure that slows the process. But if the early universe was denser, gravity might have won more decisively, allowing galaxies to convert gas into stars much faster than they do in the modern cosmos. The black holes themselves present another disturbing puzzle. Webb has detected supermassive black holes already in place when the universe was less than 500 million years old. Some of these black holes weigh millions or billions of times the mass of our Sun. In August 2025, researchers reported a direct measurement of a black hole in the galaxy UHZ-1, seen when the universe was just 690 million years old. The black hole weighed approximately 50 million solar masses, more massive than all the stars in its host galaxy combined. Concurrently, another team identified an active supermassive black hole in the galaxy Canex LRD Z8.6 at redshift 8.6, corresponding to roughly 570 million years after the Big Bang. This black hole weighed approximately 100 million solar masses and had grown rapidly before its galaxy established significant stellar mass. Most remarkably, in the galaxy GHZ-2 at redshift 12.34, less than 400 million years after the Big Bang, astronomers found evidence for an active black hole weighing about 15 million solar masses. This is the most distant black hole identified to date. According to conventional models, this rapid growth shouldn't be possible. Black holes form from collapsing stars, initially weighing only tens of solar masses. They grow by consuming surrounding matter, but this growth is limited by the energy released as material falls in. The radiation pressure can push away the very matter the black hole is trying to consume. Yet these massive black holes appeared extraordinarily early, while fully formed like Athena from Zeus's head. This has forced astronomers to consider once extreme possibilities: direct collapse of massive gas clouds into black holes without going through a stellar phase, primordial black holes formed in the first moments after the Big Bang, or early stars far more massive than anything that forms today, quickly collapsing into proportionally larger black holes. In May 2024, Webb confirmed the most distant galaxy ever observed, JWST 14.0. The light detected by Webb's instruments was emitted just 290 million years after the Big Bang, corresponding to a redshift of 14.32. The previous record holder, galaxy JWST 13.0, existed at 320 million years. Webb broke its own record within months. But JWST 14.0's distance wasn't the only surprise. The galaxy appeared surprisingly bright and surprisingly large. Astronomers detected significant amounts of oxygen in its spectrum, oxygen that wasn't created in the Big Bang. Oxygen forms inside stars and is released when those stars die. The presence of oxygen means that at least one earlier generation of stars had already formed, lived out their lives, and died, all within the universe's first 290 million years. The timeline keeps compressing backward. Every step requires time. Gas must collect, stars must form, stars must burn through their nuclear fuel, stars must explode as supernovae, scattering heavy elements into space. That material must then be incorporated into new stars. The universe's first 290 million years suddenly seem impossibly crowded with activity. Given the small region of sky searched to find JD's GSZ 14-0, its discovery has profound implications. If such luminous galaxies exist in small survey areas, then they likely exist throughout the early universe. Astronomers expect to find many more such galaxies, possibly at even earlier times over the coming decade. When the Hubble Space Telescope performed its deepest observations, it revealed nearly 10,000 galaxies in a patch of sky no larger than a grain of sand held at arm's length. From this, astronomers estimated that the universe contained a few hundred billion galaxies. The number felt overwhelming, too large to truly comprehend. Then Webb looked at the same darkness. In one of Webb's most ambitious deep field observations, covering a region only slightly larger than 3 full moons placed side by side, the telescope detected nearly 800,000 distinct galaxies, not stars, galaxies, each containing millions, billions, or trillions of stars. To appreciate this result, if you printed the Hubble Ultra Deep Field on a single sheet of paper, you would need a wall more than 13 feet tall and 13 feet wide to display Webb's deep field image at the same level of detail. Every point of light in that image represents an entire galaxy, many hosting planetary systems, all rich in dust and heavy elements forged by stellar death and birth. Webb achieved this not through some magical new physics, but by detecting wavelengths Hubble couldn't see. As the universe expands, light stretches. Ancient galaxies that appeared in visible wavelengths when their light began its journey have since shifted into infrared. Hubble saw gaps between distant galaxies not because those regions were empty, but because the light had shifted out of Hubble's observable range. Webb was built to follow that light wherever it goes. The galaxies were always there. They were just invisible to earlier instruments. If Webb's deep fields are representative, and observations in different directions suggest they are, then the total number of galaxies in the observable universe may not be hundreds of billions. It may be trillions. For every galaxy we once believed existed, there may be many more hidden in wavelengths we couldn't previously detect. More galaxies mean more stars. More stars mean more planets. The universe is not just larger than we thought. It's richer in possibility. Webb hasn't just counted galaxies, it's revealed how they're organized across space and time. On the largest scales, matter is arranged in a structure astronomers call the cosmic web. Vast filaments of galaxies stretching tens to hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form, separated by enormous voids containing almost nothing. This structure had been predicted for decades based on computer simulations and indirect observations. Webb has now observed it directly with clarity. The telescope's infrared vision penetrates dust clouds that block visible light, revealing entire populations of dusty star-forming galaxies that filled gaps where earlier surveys saw emptiness. Webb's observations show that this cosmic architecture emerged early. Filaments tens of millions of light years long already existed when the universe was only a few billion years old. Some structures were so large and so organized that they challenged expectations about how quickly matter could arrange itself. One striking example is a structure astronomers call the cosmic vine. a chain of more than 20 closely packed galaxies stretching over 13 million light-years, existing when the universe was still young. Several of its largest galaxies had already stopped forming stars, having exhausted their fuel. This is unusual for such an early epoch. It demonstrates that environment matters. Galaxies in dense regions evolve differently than isolated ones. Interactions and mergers accelerate their life cycles. But between these filaments lie voids, regions tens to hundreds of millions of light-years across, containing very few galaxies. These are not small gaps. They are the largest structures in the universe by volume. Stand at the center of one and look in any direction. You would see darkness stretching for tens of millions of light-years before encountering the nearest galaxy. Entire regions of space failed to gather matter, simply because gravity pulled that matter elsewhere. The universe is simultaneously crowded and empty. Visible matter, everything we can detect through light, constitutes less than 5% of the universe's total mass energy content. Roughly 27% is dark matter, an invisible substance that outweighs everything we can see by more than 5 to 1. Every galaxy, every cluster, every structure exists inside a framework dominated by something fundamentally undetectable, except through its gravitational effects. Dark matter doesn't shine. It doesn't absorb light. It doesn't emit radiation. We infer its existence because galaxies behave in ways visible matter alone cannot explain. Stars in the outer regions of spiral galaxies orbit far too fast to be held by visible mass alone. They should have been flung into intergalactic space long ago. Entire galaxy clusters show the same problem. Individual galaxies move too quickly to be bound by stars and gas alone. Gravitational lensing reveals the truth. When light from distant galaxies passes near massive structures, gravity bends that light, distorting background galaxies. Astronomers can map where mass concentrates by measuring these distortions. Again and again, they find mass where little or nothing can be seen. Dark matter halos surrounding and permeating every large structure. What makes dark matter essential to Webb's discoveries is its role in cosmic history. Unlike ordinary matter, dark matter doesn't collide with itself or lose energy by emitting radiation. This allowed dark matter to begin clumping extraordinarily early, while ordinary matter remained hot and resistant to collapse. Dark matter created the scaffolding. Visible matter followed, falling into dark matter wells, collecting, compressing, and eventually forming the first stars. The visible universe traces an invisible blueprint. Recently, astronomers used gravitational lensing to directly detect dark matter along the filaments of the cosmic web itself, not just in clusters, but stretched across space, threading the universe together. The cosmic web transformed from theoretical framework into observed structure. Without dark matter, the universe Webb observes cannot exist. Remove dark matter from the equations and galaxies never form. Structure never emerges. The cosmos remains a nearly uniform fog. If dark matter governs how the universe holds itself together, dark energy governs how it tears itself apart. Roughly 68% of the universe's mass energy content is dark energy, a mysterious force causing space itself to expand at an accelerating rate. In the late 1990s, astronomers studying distant stellar explosions called Type 1a supernovae discovered something unexpected. The universe wasn't slowing down. It was speeding up. Distant galaxies, were farther away than they should have been if gravity were gradually easing the expansion. The farther astronomers looked, the clearer the pattern became. To explain this, cosmology introduced dark energy. Dark energy doesn't clump into galaxies or clusters. Its density remains constant even as the universe expands. This creates a feedback loop. More space produces more dark energy. More dark energy drives faster expansion. Faster expansion creates more space. About 5 billion years ago, dark energy became the dominant influence on cosmic expansion. Webb detects its fingerprints everywhere, in the extreme stretching of ancient light, in the immense size of the observable universe, in the way distant galaxies recede and fade. Without dark energy, the universe would be far smaller. The cosmic horizon would sit much closer. Vast regions we can observe today would never have entered our view. But dark energy also determines the future. If it remains constant, expansion will continue forever. Gravity will still hold galaxy clusters together, but everything beyond them will slowly drift away, crossing the cosmic horizon one by one. In roughly 100 billion years, observers inside a galaxy like the Milky Way would see a universe filled with nearby stars and very little else. The universe would still exist, but it would appear almost empty. All evidence that other galaxies ever existed would have vanished beyond the horizon. Webb was expected to help resolve one of cosmology's deepest problems, the Hubble Tension. When astronomers measure how fast the universe is expanding today, they don't get a single answer. They get two different values that refuse to agree. One method studies the cosmic microwave background, faint radiation released when the universe was only 380,000 years old. From subtle patterns in that ancient light, scientists calculate an expansion rate of about 67 kilometers per second per megaparsec. The other method looks at nearby galaxies using Cepheid variable stars and Type 1a supernovae as distance markers. This approach consistently produces a higher value, around 73 kilometers per second per megaparsec. Both measurements are precise. Both have been repeated. Both have been scrutinized. They do not agree. Webb was expected to refine these measurements and resolve the discrepancy. Instead, Webb confirmed the higher expansion rate. The tension didn't fade, it intensified. This leaves cosmology facing uncomfortable possibilities. Either there's an unknown error hiding in the measurements, our assumptions about the universe are incomplete, or new physics exists that we haven't discovered. Each possibility carries profound consequences. The expansion rate determines the universe's age, its size, and its ultimate fate. If we're misunderstanding it, many conclusions drawn over decades may need revision. The observable universe, that 93 billion light-year sphere, is not the universe. It's the portion that happens to be observable from Earth at this moment in cosmic time. Move to another galaxy, and the observable universe changes. Different regions enter view. Others disappear beyond the horizon. Two galaxies can both be visible from Earth, yet unable to see each other. They may lie on opposite sides of our horizon. Light from both reaches us, but light from one can never reach the other. There is no privileged vantage point, no center, no place from which the entire universe can be seen. Every observer sits at the center of their own observable bubble. This creates a profound limitation. Beyond the cosmic horizon, space continues. Galaxies continue forming and dying. Black holes continue merging. Entire cosmic histories unfold forever beyond our reach, not because of technological limits, but because space-time itself prevents their light from ever reaching us. Some models suggest the universe may be infinite. Others suggest it's finite but unimaginably vast. Current observations of the cosmic microwave background show that space is remarkably flat, which is consistent with an infinite cosmos. If inflation theory is correct, the idea that the early universe underwent an ultra-rapid burst of expansion, then the cosmos could extend far beyond our horizon, perhaps into realms forever inaccessible to observation. Even this vast interconnected universe we've been describing exists only within the observable portion. Beyond it, the universe continues, shaped by the same forces, unfolding beyond every horizon we can never cross.